Hello everyone and welcome to this talk. I'll present our work on the Bayesian Skip Net as a way to integrate prior information for the prediction and segmentation of stroke lesions. To give you a quick outline of my talk, I'll begin with some background information, especially on ischemic stroke and perfusion imaging. I'll then briefly present our methods and results. Let's start off with some clinical background information on ischemic stroke. Basically, ischemic stroke is the reduction of blood flow to a certain part of the brain, resulting in tissue damage. This is a continuous process. Let's take this image as an example. So, if we have a blood clot here, preventing the blood from coming to this region, and all the downstream region here in light gray is at risk of becoming necrotic. This region at risk is called the ischemic penumbra. The dark gray region here represents the ischemic core, tissue that is already necrotic and cannot be saved anymore. However, with passing time, more and more of the penumbra is recruited into the core as more and more tissue dies off. So overall, the goal of our treatment is to save the tissue at risk and prevent it from dying off and being recruited into the core. So to be able to decide which patients we can treat, we need to know exactly which part of the brain is already necrotic and what part we can still save. To detect these regions, CT perfusion imaging is often used in clinical practice. When analyzing the voxel-wise signal over time, there are four main variables of interest. Tmax, the time to the maximum point of intensity, MTT, the median time of transit, and the cerebral blood volume and cerebral blood flow at each voxel. Currently, a threshold-based approach is used to define the tissue at risk by selecting regions with a time to maximum intensity exceeding 6 seconds and by defining the already necrotic tissue as a severely reduced blood flow. So to summarize, we have our acute event and then we perform perfusion CT imaging to detect what is still salvageable. Based on this, we decide to initiate treatment, but it's only a few days later that we know the extent of the final lesion. So generally, we are here. We have our stroke patient, we have performed CT perfusion imaging, and ideally, in order to decide what treatment to give to this patient, we would like to know the extent of tissue at risk, what part is already necrotic, and what part will die even if we treat our patient. In recent years, many machine learning models have been developed to address these issues. In other words, to go further than just threshold-based segmentation of the core and also to predict the extent of the final lesions. Although most work on the segmentation of the core has been done on diffusion weight imaging in MRI, since the release of the IELTS 2018 dataset 2 years ago, there have been some great submissions in this field. Most rely on a UNet backbone and try to segment the core based on perfusion CT imaging. For the more complicated task of the prediction of the final lesion, most work has also been done on MRI, but a variety of models have nonetheless been proposed, ranging from CNNs to gradient-based tree models, as well as very recently an attention-gated UNet. So now we have these models, be it to enhance the segmentation of the core or predict the extent of the final lesion, but we also have this threshold-based approach, the threshold-based segmentation of the ischemic core that is not perfect but has been largely validated in clinical studies. So the question we asked ourselves was, couldn't we integrate this information that is contained in this segmentation in our models? That way, our model would simply have to refine the segmentation of the core and would have a starting point for the prediction of the final lesion. Lucas and colleagues have done some work in this direction, as they used a manual segmentation of both the ischemic core and the tissue at risk, from which they derived a deformation model that was modulated by a CNN that had the perfusion images as input, and this modulated deformation model was then used to predict the extent of the final lesion. And this worked very well on a small sample. To build on this, we formulated two questions. One, couldn't we get our model to learn this deformation by itself, so to learn the divergence from the ischemic core? And two, couldn't we use automated prior segmentations based on clinically validated thresholds? To address the first question, we propose a novel model we call the Bayesian Skip Net. Basically, we used an attention-gated unit as initially formulated by MICCAI and colleagues as a backbone, and then that takes here the perfusion images as well as the prior segmentation as input, and then we add a novel skip connection that passes down the unchanged prior until the very end of the network. In this way, the main network, this lower grade part here, has to learn the divergence from the prior, marked in red above. The prior is then reintegrated at the end right there. To reintegrate the prior, we used two different models, or two different methods. Method A via summation and method B via convolution. To obtain the prior segmentation that is needed for this to work, we used the method that is generally used in clinical practice and well defined in the literature, meaning we used the cerebral blood flow, applied some smoothing, normalized by the contralateral mean, meaning the mean of the contralateral hemisphere. And here you can already see in this center image where the colors have been adjusted, we can already see that there are some regions with relatively low blood flow. And then we apply a threshold at exactly 38% relatively to the contralateral hemisphere. To remove a few sources of noise, we simply remove the skull, the CSF, and the major blood vessels. Now that we've defined a model taking both perfusion CT and a prior segmentation based on a threshold approach as input, we evaluated it on two distinct datasets. First, we evaluated its performance on the Geneva stroke dataset on the task of prediction of the final lesion. This dataset has 144 patients with acute CT perfusion imaging, and on a follow-up MRI, the manual segmentation of the final lesion after treatment. We then further investigated the performance of our model on the segmentation of the ischemic core on the IELTS 2018 challenge dataset that I already mentioned, comprising 94 patients with the manual segmentation on acute MRI before treatment. So here we're trying to segment the ischemic core. Now, to evaluate our proposed model, we benchmarked it against the attention-gated unit that was used as the backbone, here labeled as simply unit, and against the prior that was used as prior segmentation. We used a classic three-way split, and the best model was selected on the validation subset. As you can see on this slide, on the Geneva stroke dataset, so on the prediction of the final lesion, our model using method B, so convolution, but not method A, summation, to reintegrate the prior, outperforms the baseline model on both dice and precision. This, however, comes at the cost of a lower recall score. Now, for the second task, meaning the segmentation of the ischemic core on the IELTS 2018 dataset, we can see that our model with method B performs very similarly than the baseline on the validation set, but manages to generalize better on the test subset. Here you can see that it outperforms the baseline on the test set in all three metrics. Method A was not further evaluated as it did not yield any improvement. We then proceeded to compare our model to the top 3 submissions in the IELTS 2018 challenge, although this analysis is somehow limited as we did not use exactly the same test subjects here. We can still conclude that our model performs similarly or even favorably when comparing against these top performing models. To show you what this means in practice, here are two subjects, A and B, from the Geneva stroke dataset. In yellow, you can see the ground truth segmentation of the final lesion, so this is the more complicated task of prediction of the final lesion. And in brown-orange, you can see the model prediction. On the top row is the baseline attention-gated unit, and on the lower row, you can see the unit with method B, so our proposed Bayesian Skip Net with method B. Here, for example, on subject B, you can see that the model manages to focus better on the lesion and reduces the false positive rate. And for subject A, here on the left side, we can see that our proposed model manages to segment some of the regions that are otherwise falsely labeled as negative. We further looked into the speed of convergence of the evaluated models. As in theory, starting with a prior would have our proposed model less information to learn and thus should converge faster. And as you can see here on the training curves, so here you can see the loss plotted against the epochs for both the trained subset and the validation subset of the IELTS 2018 challenge. You can see that our model with method B here converges a lot faster than the baseline unit. This seems to confirm our hypothesis that there is less information to learn for a proposed model. So overall, we can say that integrating this prior segmentation obtained by a threshold-based method that is clinically validated seems to be a good idea, and that our proposed model, the Bayesian Skip Net with method B, so convolution, manages to effectively leverage this prior information to improve performance in both segmentation tasks, so the segmentation of the ischemic core, and increase its performance in a stroke prediction task where you have to predict the extent of the final lesion. Moreover, it also improves model convergence. As future work, it would be great to see if adding a prior segmentation of the penumbra would yield an increase in performance. And as prior representations are common in many medical problems, it would be great to see if this model could also be used in other applications. With this, I would like to thank you for tuning in into my talk. And if you have any questions, please do not hesitate to contact me at the address that you can see below.